So I had the chance to talk to some of you. Is it too loud or it's okay? In the morning, and I realized that it's a different level of prior knowledge that you have of the subject. Some of you might know many of these things that we will be seeing here, or at least some of these things of the first two lectures. Others would not, but I think, as Enrico Fermi had once said, that it's always a pleasure to listen to something we already know. So I think it will be useful and helpful for all of you anyway. Okay, I'll start talking about gauge field theories. Some of these things I will go a bit slowly, and you probably have a wrong impression that it will always be like that. And especially when there are simpler examples to convey a message, but others will go a bit more fast. So just keep up the pace in that sense. So let's start with the gauge principle. We know that the standard model has 3 interactions in it, and all are gauge field theories. The idea of gauge principle came quite some time ago, about 100 years ago, although we knew of a gauge theory even more than 200 years ago. So there is these couple of articles that you can find on the net, which are quite useful. Historical Roots of Gauge Invariance by J.D. Jackson. And then David Gross gave a talk on C.N. Jiang's 70th birthday on gauge theory, past, present, and future. So this first article, which is by J.D. Jackson, if you look at the abstract, it gives it starts talking about the roots of gauge invariance, which go back to year 1820, when electromagnetism was discovered. And the first electrodynamic theory was proposed, and then talks about some particular gauges in which in which Maxwell's equations were studied. But the interesting part, which will be particularly useful for us, will be this. In 1926, a relativistic equation for charged spinless particle was formulated by Schrödinger, Klein, and Fock. You all have seen quantum mechanics. You know Schrödinger equation, which is non-relativistic. But probably some of you wouldn't know that Schrödinger, before giving his equation, had already worked on a relativistic equation himself. But it didn't work out so well because it had problems of interpretation. And then he realized that his bigger task was to explain the hydrogen atom. And when you look at the speed of an electron in the hydrogen atom, it is about 2 orders of magnitude less than the speed of light. And therefore, the relativistic corrections, which are of the order of v squared over c squared, will be 10 raised to the power minus 4 suppressed. So he restricted himself only to the non-relativistic description of that. But then there were other people working on it as well. And it was later discovered that this equation is invariant with respect to the multiplication of the wave function by a phase factor, wave function of the fermion, with the accompanying additions to the scalar potential, which is the electric potential and the vector potential for magnetic field. And then while proclaimed this invariance of the general principle and called it this name in German, which is translated as gauge invariance in English. And then the non-abelian gauge theories were introduced by C.N. Jiang and R.L. Mills in their paper, I think, of 1954, in which they talked about SU2, because still there was no knowledge of SU3. People had already seen some of the SU2 groups in physics that I'll talk about later. So Maxwell formulation of electrodynamics was perhaps the first field theory, which had good qualities, but were really rediscovered or appreciated much later. This had Lorentz invariance, but it was really not appreciated so much till the advent of the theory of special relativity. And then it had gauge symmetry in it. And in fact, gauge symmetry became a bit more important even about 2 decades later than theory of relativity, and about early 1920s, 1926 or so. So with the advent of quantum mechanics and theory of relativity and the gauge principle, people were more interested in it, although this formulation of Maxwell's equations was already having in it Lorentz invariance and the gauge symmetry. In 1929, Weil showed that electrodynamics was invariant under the gauge transformations of the gauge field and the wave function of the charge field simultaneously, more formally. And in 1954, Yang and Mills studied the gauge principle and non-abelian field theories. Okay. So this was a paper on U1. And this paper, as I was mentioning, by Zhang and Mills, it talked about SU2 local gauge transformation. SU2 was known, people knew about the spin up and down of the electron, and that has SU2 symmetry. Then since the work of Heisenberg in 1932, people also knew about isospin, that proton and neutron were isospin partners. And therefore, there was contact of SU2 spin. In fact, I think he mentioned both of these isospin and as well as spin. And he realizes that when you do SU2 local gauge transformation, then you can come out with 3 gauge particles, just like you do with the U1 gauge transformation in quantum electrodynamics. Okay, so I will now, after this introduction, quickly go on to onto the Dirac equation. So we will understand that you all know, you have seen the Dirac equation, you know what gamma matrices are, you know a little bit about gauge transformations and all that. Anyway, we will to start with not go very fast. So this is the equation of a free Dirac Lagrangian. It corresponds to all the particles with spin half. Electrons obey these equations, quarks obey these equations, muon, tau, all of these fermions obey this equation. Now this is something is not coming out exactly with the presentation, but I think that hopefully it will not be. No, it's not. Yeah, it gets cut off a little bit, and the sentence goes to 2 lines instead of 1 line. But I hope you can read it. No, it's okay. Anyway, I can pass on to you the presentation as such. Yeah, something is not okay, but I hope it goes well. So what we can see is that it is invariant under abelian U1 gauge transformations. What simply means is that if this is the fermion field, and if you transform it in this manner, in which there is an exponential time minus I alpha, where alpha is a real constant, then this equation does not change. Okay, the psi will change. There will be an exponential factor coming here, and this psi bar, as you know, is a psi dagger gamma 0, and therefore this will make a complex conjugate of this exponential factor. There will be exponential plus I alpha sitting here, and therefore they will cancel each other, and the equation will remain invariant. Now, what I'm not going to talk about is another theorems or conserved currents and charges. It's not of direct relevance to the article, but what I want to tell you is that whenever you see something of this color, which is something like orange or rusty, that means that that's an exercise for you guys. So I would very much like that when you go home, then you can try to solve these exercises, and if there is a problem or something, you can always ask someone else who has done it, or ask me. So it is find the conserved current and charges corresponding to this conservation, this global symmetry which is there. Now, what we demand is generalizing this this global symmetry into a local gauge symmetry. What it means is that let's demand that this would be a symmetry even when this alpha depends upon space-time coordinate x. Okay. One can show that the mass term in the Lagrangian is still invariant, because this is m here and this exponential factors will again cancel out, but the kinetic energy term which comes from this these derivatives will not, because this derivative will now not only act upon the wave function, but also on this alpha. And therefore, there will be a dimensional term which will violate this symmetry. However, we know that this invariance can be reinstated if we introduce a gauge field and a corresponding gauge covariant derivative. Okay? So we introduce a gauge field A mu and introduce a new covariant derivative where this field will be interacting with this fermion, and the strength of that interaction is given by this coupling or charge which couples this fermion to the gauge field. So the starting point for us will be this new Lagrangian with this covariant derivative term, and this will now be invariant under simultaneous gauge transformations of the fermion and the gauge fields. And these transformations are something like this. So this alpha now depends upon the space-time coordinate x, and both the fermion field and the gauge field change simultaneously. Therefore, this field, the change in this field contains the same function alpha, so they know each other. Something like this. The change in the equations of motion of the Lagrangian is being compensated by this change in the gauge field, and that's what ensures that the Lagrangian is still invariant. And the idea was to achieve the following. Remember that if we go back for a second, what was causing the problem was this term, which comes from an exponential. It's because we couldn't factor out the exponential term from this derivative because of this derivating introducing another term. So we have used this transformation in order to achieve the same thing. So this is the covariant derivative, and the transformed function is such that this exponential factorizes out onto the left side, and therefore the Lagrangian is invariant, and that's pretty simple to see. And therefore, we can see that this term is invariant under the simultaneous transformation of these two. Now, when we reach up till here, it's okay. We have needed a field to do that, a gauge field, a spin one gauge field, but we don't have yet the dynamics of that field. Okay? But we knew already at that time, we knew Maxwell's equations, we knew that there was a gauge field A mu. So you could identify this new field with this gauge field, which is present in the Maxwell's equations. And if you do that, then you can simply add this Maxwell Lagrangian into it, F mu nu, identifying this A mu with what is present here. And therefore you have this Lagrangian, which is the Lagrangian of quantum electrodynamics in that. Okay? If you were working only with the Maxwell equation, you didn't need to have this factor of 1/4 there. But now that these fermions are present here and the relative interaction terms, because these are the fermions which generate the currents for the Maxwell equations, so the factors should be correct, and therefore there is a factor of 4. There is some other terms like gauge fixing term. I'm not going to talk about this for the time being. So the idea is something like that. If we look back at what is happening, one thing I should tell that when, sometimes we try to understand what the equations are telling us or talking to us, when we try to visualize, not everything is completely 100% correct. So be aware of that. Just look at the idea, especially when you go to the non-abelian part, it will become a bit more complicated. So you know that wave function of electron is complex. It has a real part. It has a phase associated with it. And you see that what happens in global gauge transformation when your alpha does not depend upon the space-time point. So if you imagine that these represents different space-time points, and if you imagine to start with that their phase is all pointing in one direction, it could be different as well, but that's for the sake of simplicity. So what the gauge transformation is doing is that we are changing the phase at every space-time point in an identical manner. Okay? And that is what ensures that the Lagrangian and the corresponding equations of motion remain the same. But when we demand local gauge invariance, that what we in practice are doing is that we are having this freedom of changing the phase at a different space-time point randomly, differently. So that doesn't allow the Lagrangian to be invariant anymore, and therefore we have to introduce a gauge field. And as I was telling you when we were looking at the equation, that the gauge field knows about this phase transformation because it changes itself according to this alpha of x. And therefore, somehow what is happening here is compensated at the same space-time point by this field. And if this is going in this direction, it compensates by the corresponding transformation of the gauge field, so that the Lagrangian comes out to be gauge invariant. Now we can go on to complicate life a little bit more. We can go to an SUN gauge theory. Sometime I will just use it, how do you say, interchangeably. I will sometime talk about SUN, and sometimes suddenly I'll talk about SU3 as a particular example. So just watch out for that. So for the moment, it is an SUN and field instead of just three colors or just one electron field. There are n fields. It probably should be n capital. Now, it is also invariant. The initial Lagrangian is, of course, the same as the Dirac Lagrangian. It just has more components to it. It's invariant under an SUN transformation, which is this transformation. Okay, these are this function now goes to a new function, but using the generators of the SUN group, and these generators are n squared minus 1 in general. Right? So again, if these parameters, which are n squared minus 1, are independent of the space-time point, the Lagrangian is invariant. That's all. Now, before I go on to do this, the idea, of course, of the gauge principle is that just demanding the local gauge invariance of a certain group, you're able to generate the interactions. Now, that is, in electrodynamics, it is very simple because there is just one interaction term present. It's just the photon interacting with an electron. But when you go to an SUN gauge field, then it doesn't entirely generate all the possible interactions. You have to add the dynamics and interactions afterwards, but still respecting the gauge invariance of those. Yes. 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 In fact, we will we'll try to figure out how to define the field tensor with the covariant derivative in such a way that you have this gauge invariant terms. It will be a bit more involved here for SUN interactions. So this is still, these are thetas, and I think that these are still not depending upon x. As I was telling about this generators, these are n squared minus 1. These are n by n matrices in n dimensions. Unfortunately, yeah, this is, probably we'll try to see tomorrow if we can manage something better. Maybe I can bring my computer or something. Yeah, we can try that as well. Yeah, it's all overlapping here. I don't know how bad it can become. And in fact, these generator, we can write them in matrix form as well, do not commute. And every SUN and group is in fact defined by what these are. In for SU2, these are epsilon ABC, or and for others, SU4, SU5, these are all different. So an SUN and gauge theory SUN group is uniquely determined by what these structure constants are, F, A, B, C. Now here the picture is not exactly the same, but the idea will be something similar. So imagine if there are color phases associated with different space-time points, and we start this. So a global transformation will be that you will transform each of this phase exactly the same in all space-time points. So if this is one of the phase, you are transforming in exactly the same way at all space-time points. Then you have the green one, it also goes in the same direction for all of them. And then there is this blue one, and that one, we have moved it only a little bit, but identical in all space-time point, but all of them separately can be different. Okay, so that's the idea what I wanted to convey. So that what happens in global gauge transformations, and they're transformed independently of X, each of them separately, and hence the Lagrangian is invariant. And now, we make life a bit more complicated, and we want to see if we are able to generate the interactions which we know now are the QCD interactions through demanding the gauge invariance under local transformations SU3. So that's what is done. We have this operator here, and just remember that this operator U is this exponential. Okay. So this tau, of course, when you're talking about a particular n, will change its form, and it's also generally dimensions. Okay. Now what we see is that we can't have just one field. What we need is n square minus 1 gauge fields to compensate for this different phases that we have introduced at different space-time points in order to ensure that the Lagrangian is still gauge invariant. Okay. So that's what is happening. The new covariant derivative we have to define in this fashion. At the same time, this A mu having this particular gauge transformations in order to ensure that your new Lagrangian is, I think that was something like the question was. We'll come back to it actually a bit more in detail. So, and the gauge field at the same time transforms in a particular manner. Okay. So, so these are the, this is tau A mu A. These are 8 fields for SU3. In general, these are n square minus 1 for an SUN gauge theory. So it transforms as such. This is the U, the exponential factor or operator that I had mentioned you to remember. This is U. This is U inverse here, and then as in the case of U1 gauge field theory, it knows about the local phase transformations by this parameter that is governing at different phase times. So it provides the right compensation. So we have to do that. Okay. Now, if we do that, then it ensures that again, this covariant derivative, when transformed, it takes this exponential factors on the left. That's the whole idea to do in order to make sure that the Lagrangian is. So that's the game that we want to play so that is achieved. And that, if I'm not wrong, is a unique way of doing that. So that ensures so I think we can, here there are a few steps. You can see how they are done. It is just a reminder to you that the first line is already what was there in the previous slide, how the gauge field transforms. And then you want to see if your covariant derivative, it's the covariant derivative here. Okay, that's it will transform. Therefore, the A mu transforms at the same time as your psi field transforms. The field side transform with this U of theta, and we know that this whole thing transforms as such. And therefore, what you're doing is what's happening here. So this d mu will operate upon both of this. The first term is which is operating upon psi, and here U theta is left alone, and then you have here operating upon U and nothing happening to the wave function. And then it is in the other part what's happening here. So what you see is that this is transforming, and therefore what I have to use is this thing in the prime and this thing. So when I use this thing, you have this U of theta here, this tau which comes from here, this is U inverse, and then this U of theta psi. And this U inverse U will give you 1 here. And then you have this last term. You'll see this I over G will multiply this IG, G will cancel, and then you have a minus sign, and these are the corresponding quantities that will appear again. U inverse U will give you 1, and therefore this term will actually cancel out with this term, and then you are left with this term, and then this thing simplifies such, and therefore you simply have U of theta sitting on the left side because there are unity operators coming here, and you're able to, factorize it onto the left side, which ensures that your Lagrangian is cage invariant. So in this thing, what has happened in the local gauge transformation is that you take each of the phase associated and you transform it randomly. Randomly means as a function of x at a different space-time point. Each of the phase, here it transforms here, at a different space-time point, it is transforming differently. Here it is differently, and here. And the same thing as red and green. They're all. So in that case, I've come back to describing SU3. What you have to do is to introduce compensating field, and you will eventually find out when we come back to it that if these, you associated 3 quarks with 3 colors with every quark or fermion field that you are studying, then you'll have to associate these color anti-color with these each of this field in order to ensure that this thing happens. So that's what it is. Now, what makes quantum chromodynamics so different and so problematic is what we are going to see the first glimpse of that now. But for that, I'll just try to. At what time we started? 2:30, was it? Oh, okay. So what I'm going to try to recall exactly how could we form this F mu nu. Remember that I was just a bit lazy and say that F mu nu, we know that there is Maxwell's equation, and we will identify the dynamics of the photon field with the field that appears in the Maxwell's equation, and then just use that to complete our Lagrangian. But there's a formal way we can try to do and introduce the dynamics of the field, of this F mu nu field. So that's why I'm trying to go back to the example. There are many times we will revert back to quantum electrodynamics because there you can see things a bit simply, and then we can complicate for QCD and other gauge field theories. We know that F mu nu is invariant under the gauge transformations. It transforms like this. Yes, the gauge field transform like this. And this is the same transformation as U1, and you can see that we had seen this transformation, but you can rewrite in this form. It's the same thing. Okay, what we can check here is this identity. This is quite easy to check. Let me see. This is the covariant derivatives here. This d mu d nu minus d nu nu mu. Operating upon the fermion field will always give you I, and this is the coupling, or along with the generators, whatever be the group generator will be, times the field tensor associated with the gauge field. And this definition goes beyond U1. For SU2, SU3, you will see that it's come out to be the same. So this is something that can more or less help you find out what this F mu nu is. Now, we know that this is the covariant derivative. So we insert here d mu and d nu, and this in the reverse order here. And what we see is that when we do the expansion of this is partial mu, partial nu here. And the only thing which will change is that if there is a partial mu here, there will be a term where it will operate upon this A nu field other than the psi field. And that will introduce derivative of the gauge fields here. So the only terms which will survive in the end are these two terms, and all the rest will cancel each other out. Now this is crucial for our own existence. What is crucial is that these terms which are here, which are quadratic in E square, they happen to cancel each other out. Okay? And U1 is the only place where we'll see they cancel each other out. If they had not canceled each other out, we would have photons which will interact with each other. There will be self-interactions of photons, and life will not be the same as we live today. So in the end, this F mu nu is this. As soon as there will be other gauge fields coming from any other SUN group theory, this is no longer going to happen. So we can now want to have a couple of identities. What we can show is the following: that when you transform this whole thing, then basically your exponential again comes out on the left side. And I'm not going to look at it because I want to spend my time on something else a little bit more. These are just, you will have the presentation with you. You can have a look at it. Each of these things transform, and we know that this transformation, the only thing it does is ensures that the exponential goes out on the left side. So it does it once, and then it does it second time. And this identity is easy to prove. The whole idea was d mu, introducing d mu, was to have this exponential on the left side. So it does it in 2 steps. Okay. And then you have, so these, there are a couple of these identities, along with this fact that when you transform this thing, a gauge transformation, the whole thing on the left and right will transform. And that allows you, if you put all of these things together, this thing is equal to here, and this thing, if you substitute this thing and then you use this, you will see that this transformations take place. And because F mu nu just has, it doesn't have matrices in it like Dirac matrices, and therefore this can go around here and there everywhere. What I want to see that if you have this expression, this exponential of minus I alpha x will go on to the right, because the derivatives here only are acting upon the gauge fields. So I can move this here, and this is psi prime x. And therefore, you can prove from here that your F prime mu nu is the same as F mu nu. We had already shown this, saying that F mu nu itself is gauge invariant. Okay. Now we have here proven it slightly in a roundabout manner that it is gauge invariant. But the reason is that, again, we are lucky is that it's only in U1 that you'll find this field tensor will be gauge invariant. It's not the same thing in others. So F mu nu for SU3 is not going to be gauge invariant. Here we are good, it's gauge invariant. So if we have to put it in a Lagrangian, the only thing we have to do is to make it Lorentz invariant as well, because we know that the Lagrangian should be Lorentz invariant. And therefore, we contract it with another F mu nu, and here is our Lagrangian. And we also know this way we have been able to generate what its form will be using this identity, which I told you would be valid for other gauge groups as well. So here we have formally been able to see what F mu nu would look like, that it will be gauge invariant, what will it be explicit form, and you only have to make it Lorentz invariant to put it into the Lagrangian. Now we, of course, go on to make life more complicated for ourselves. We go to SUN, we have the color fields, yes. Yeah, 1/4 and the sign we come because we want the Maxwell's equations to be, quantum electrodynamics to be recovered, yes. That's where we make the connection with the physical world. Yes. Now, how do we define F mu nu if you're going to SUN? Okay. Now, one could, of course, as a first guess, say, okay, we have this experience. Let's just do it. These are color indices, which comes from the generator. We don't put it in U1 because there is only one generator. So these are. So, but if we try this, it will not work. We'll see that this thing is not gauge invariant. It doesn't work. And therefore, we have to resort to this general formula that I had told you we had invented in order to be able to define this F mu nu A. So this, what we had seen just now, was for U1. There was just IE here, but now that we have this generator for SUN, we have IG and this tau A over 2, and these are the generators of the group. So if we are able to solve this, then we will know what F mu nu would be. Okay. Now this is a slightly a longer thing. Still, it is not. In fact, I myself, when I look at each time, I can't figure out where I go from here to there. Okay, so if I try to explain to you, I'll probably get lost myself. But I have tried to provide myself some helping hand, which term cancels with which term and where it goes or not. But the idea is this, no? I think the first line to second line, I've made myself a bit more complicated. So this terms come from this partial mu with partial nu. Okay. Now this term comes from second term here and the first term there. Okay. So this is this and this is this. And this thing comes from this derivative operating upon this and multiplying with this one. And this term comes from when this partial mu operates upon this and leaves the wave function as such. And therefore, this comes simply by multiplying these two fields. Okay. So these are all the terms, and these are all the terms here. We had very similar terms in U1, but we realized that all terms had canceled each other out. Here, unfortunately, because these generators do not commute, and therefore they don't cancel each other out. And that's one of the biggest thing that will happen. So still we have a lot of cancellations taking place. This red cancels out with this red, this blue cancels out with this blue, and therefore we are left with this. Now, I just have to simplify a little bit. I would like, because you can see that A and B are dummy variables. So because I would like to express all in terms of one of these, wherever this B was, for example, here I just call it A. And therefore, the first two terms, this term and this terms, only have A index because I have, used this freedom. Here, it's not easy to use the freedom because I have to make sure this commutation relationship. So the first step is I simply take these things common out and then use the Lie algebra commutation relation and write it in terms of F, A, B, C. But now that I have reached this point, what I have just simply used is that, all these are repeated indices, A, B, and C. These are dummy variables. So I change C by A and A by C. Okay. So what was there before C, I would call it A. Okay. And what was A, I would call it C. Okay. So this has become A, but you know that this is now CBA. But because it is completely antisymmetric, I can move it twice back and forth, and therefore it will not, I will just replace it and it will not change the sign. Eventual sign will be the same as minus. And the reason I have done this is that now this tau A is common in all these terms, and therefore I can factor it out on the left side. Right? And now that I factor it out on the left side, what is left inside is this, and that gets then identified with this gauge field tensor F mu nu A. Okay. Now, that is, of course, different from U1 gauge field theory, but that's quite interesting because these things now no longer cancel. And these are the terms which will be the origin of interaction between the gauge fields in SU3 and also in SU2. The self-interaction that you will see among gluons or the Ws at bosons and SU2 gauge field theories will come from this thing. Okay. So here we can identify that F mu nu A would be this. Now there is some homework that you want to see is, interestingly, the first thing you want to see it is gauge invariant, and you will see it's not gauge invariant again. Although the whole idea was to try to do that. But you will find that it has its own gauge transformation that I'm not going to do it. That's your homework. Okay. But what you will be lucky with is that when you contract it with another F mu nu A, that thing is gauge invariant. Okay? So that's good because that's the thing which is going to enter the Lagrangian. So you're safe. So that's what you put there. This thing is gauge invariant, and then that's how you will add this. And if you explicitly write it out, then it has several terms in it. It is quadratic terms, which I have not written, but then there are terms which are, oops, no, you can't be doing that. It's my son. You have to wait. Oh God, how do I? No. Give me a second. So these terms will tell in the Lagrangian that there will be 4 gluons interacting with each other, or 3 gluons interacting with each other, etc. Okay. So the whole thing, it is still not the whole thing, because QCD becomes a lot more complicated after that. But the basic interaction, the basic idea is still there. You have the gauge fields here, and here are the fermion field, and here hidden inside this d mu covariant derivative is the interaction between quarks and gluons. So what you have seen, that what basically this gauge principle has done for us is generated the quark gluon interaction. But then we had to find and devise our own ways to generate the interactions between the gluons in a particular manner, the self interaction. And these are actually not even enough, because then if we are working with what is called the covariant gauges, you have to introduce other fields like the ghost fields, and then you have to have the interactions of those fields with gluons and quarks as well. But anyway, the upshot so far is that we have gluon fields. They're massless, spin-1 bosons. A lot of these things will be seen during the whole set of lectures. Here we see they're massless, but they will no longer remain massless by the end of these lectures. Okay, and we will see how that happens and what are the consequences of it, and why people fight with each other by saying whether they are or they are not. So we'll come to that, but I'll make them massive at some point. They're spin-1 bosons. They're color octet because the group contains 8 generators. They're flavor singlet, that is, gluons are flavor blind. I've not talked about anything about flavor yet, but suddenly instead of the psi field, I have introduced this index here, F. That means that I'm already having in my mind that this QCD Lagrangian has these fermion fields, and those fermions can be different quarks. They can be up quark, down quark, or strange quark, or charm quark, bottom quark, top quark. And therefore, each of these names will correspond to a different flavor. And therefore, this flavor corresponds to whether it is an up quark or a down quark, or what kind of a quark it is. Okay. Yes. It's gauge invariant. Yeah. I mean, it itself is not, but yes, that will always happen. It's only for U1 that it's not going to happen. Now, I don't know why I'm exactly showing this, but when you have seen some images, they stay in your mind. I was talking when I was here. I just mentioned that these terms in the Lagrangian indicate that there are 3 gauge fields interacting with each other. This will tell that there are 4 gauge fields interacting with each other. Then there are terms before where there is 2 gauge field. There is 2 fermion fields and a gauge field. That means there is a quark-gluon interaction there. And all this, there is a huge step between knowing a Lagrangian, then making a quantum field theory out of it, then doing an S matrix, then doing its expansion in perturbation theory, and then identifying those terms with what we call the Feynman diagram. So there is a whole course missing between showing you a Lagrangian and then showing you the Feynman diagrams. But you have to live with it. And then there is the I epsilon things which have their own interpretation, but I'm not going to go through any of this. So you just imagine that once we know the Lagrangian, and if we know the corresponding Feynman diagrams, then we can put those Feynman diagrams in different kind of physical processes that we observe in labs here or labs anywhere else. Scattering processes, you can calculate cross sections, and from there you can decipher various quantities that physical observables that when. But one of the principal things behind these Feynman diagrams is that as soon as you start talking about a Feynman diagram, you're already assuming something about your gauge field theory. And that assumption is that the charge E that appeared there, which governs how strong is an interaction between a photon and electron, or the charge G, which appeared between, which represents the interaction strength between a quark and a gluon, we assume that that quantity is small, is so small as compared to 1, that you can expand your amplitudes or your cross sections that you calculate in a perturbative expansion. And Feynman diagrams are the fundamental building blocks of that perturbative expansion. Okay? Now, as we all know and do hadron physics, we know that one of the problems of hadron physics is that there will be a part of QCD regime in which this coupling is not going to be small. So whenever it's not going to be small, this Feynman diagram paradigm is going to completely break down. For values where G or E in electrodynamics will be approaching 1, this will not work. In fact, one of the most interesting thing we will see hopefully in lecture, I still have 2 hours now.
Yeah, more if you want.
Well, I'm taking up the spot of the previous person as well, no? What time is it?
I don't think so. I think you were just exchanging, right?
No. Okay. No, space is okay. Just tell me the time. No, I mean, what time is it now? It's 2:30? 3:15. I have 15 minutes. Okay, good. So that will completely break down. And what we will find interesting, and we'll probably see it in lecture 3, I think, is that even in quantum electrodynamics, which is the simplest of theory, if your coupling was not 1/137, and if it was the order 1, you wouldn't be able to do Feynman diagram expansion. And not only that, you will see that your quantum field theory generates new solutions which are not observed in perturbation theory. And that is the whole thing which is related to this course of non-perturbative study of quantum chromodynamics. You'll see that it's not only QCD, it will work also in QED had we lived with a QED which would have an interaction strength close to 1, where perturbation theory breaks down. So here we are doing a perturbative analysis so far. We will go a bit far today and tomorrow, and then third lecture, goes to the non-perturbative solution. So this is something like, hopefully you have seen how a photon or a gluon propagator looks like when you insert into a bigger picture of a bigger diagram of cross sections and things. And this is an electron propagator. If you don't understand it so well now, we will look at it several times, so it's not a problem. Psi or p squared. These are color factors A and B, and yes, I think when I put these capital letters here, it just means that this corresponds to the adjoint representation of the color group. So these go from 1 to 8, and when these are small a, b, they go to 1 to 3. Okay, so the quark color goes from 1 to 3, and the gluon color goes from 1 to 8. I think, if I'm not wrong. I don't remember so well. And then there are interactions, so 3 gluon interactions and 4 gluon interactions. These are the structure functions which corresponds to the SUM group that you're studying. This interaction is extremely problematic within perturbation theory or non-perturbatively, you will see, because these structure functions and these Lorentz indices completely mix up. This is the same thing which factors out from all the Lorentz indices and fits apart. Okay? This doesn't fit apart because this is a different product which appears for a different combination of Lorentz indices and a different combination for another combination of, and that makes life extremely difficult. I don't know if I'll be able to explain it exactly in this set of lectures, what problems it causes in the calculus. And then, of course, we have to introduce this ghost field for particular reasons that we are working in covariant gauges, and therefore we will have this ghost which is only a mathematical artifact for doing our calculations, interacts with gluon, and then there are of course quark gluon vertex, which is one of the most important vertices in QCD, and it has on Feynman diagram rules associated with it, and that's it. Now, that is all fine. You can have a Lagrangian, and once you have, from classical mechanics, you have your equations of motion, and you can solve them. Okay. The same thing you can do. You have a Lagrangian. Here, the easiest thing is you make Feynman diagrams, And you can do that amplitude calculations, cross-section calculations at the tree level. Okay? And then you compare, and most of the results in quantum electrodynamics come out to be very good. But that stopped working in 1940s. From 1925, when electrodynamics were more or less born, till about 1945, everything was happy, happy, joy, joy. But it stopped working. It stopped, actually, people started worrying about it in 1930s, that whenever they tried to make the calculations more precise and what we call as higher loop calculations beyond tree level, we find out that the results were not finite. And theoreticians knew in 1935, 36 that it's not working somehow. So it was born in 1920 through the works of several people, Born, Heisenberg, Dirac, Pauli, Feynman, Schwinger, and many others, actually. And so I was telling you that in late 1930s, QED calculations had already revealed that they could only be done at tree level. We have come back to quantum electrodynamics. Okay, we will keep moving back and forth. QCD is still not invented in 1939. So these infinities emerged at higher orders when you go to loop calculations. In fact, in 1940s, precise measurement of the levels of hydrogen atoms, which is called the Lamb shift especially, and the magnetic moment of the electron, exposed these discrepancies. It was done first in 1947. An experiment revealed something that could not be explained with just the tree level Feynman diagram calculations. And therefore, these new works had to be done. I think I'll just try to mention it something very briefly. It will be very important there that this whole saga in which you have to, when hydrogen atom, when you study the transition between different levels, and we didn't understand properly in 1940s. And when we tried to understand it, it gave birth to renormalization, a whole new understanding of quantum field theory. One of the things that is done here in Jefferson Lab is that you do similar studies, but of strongly interacting bound state, which are like mesons and nucleons. And you try to study how are the transitions that take place from nucleon, for example, to its excited states. It is like in the hydrogen atom, an electron goes from one state to its higher state. And the understanding of this transition in hydrogen atom really showed us how quantum electrodynamics works to the deepest levels. And these studies of transitions of mesons and baryons from its ground to excited states, we expect will give us a lot of information, not only on perturbative, but especially on non-perturbative quantum chromodynamics. And that's what some of you will be doing eventually. So this work was done by Feynman, Schwinger, Tomonaga, and Tomonaga had done it about 5 years earlier than other people, but he had published it in a Japanese paper, I think, and eventually they got the Nobel Prize. Here you can see 1947, there was a conference held in Shelter Island in June, early June. And the only person who neither is worried having his hand on the head or the face or holds a paper is an experimentalist. It's a Lamb here because he has already done the experiment and he says there is a discrepancy and all the theoreticians are trying to work out what's happening. This is Feynman here, this is Schwinger here, this is Wheeler here, and they can't figure it out yet because it's not working, their calculations, renormalization. So this is called Lamb shift. According to Dirac and Schrödinger, if you look at the normal quantum mechanics, if there are states with same n and j quantum numbers but different L, they will have to be degenerate. But this experiment of Rutherford and Lamb, it's not Rutherford, it's a different guy, it's a student of Lamb in 1947, showed there's these two states which have the same n and j, but differ in L because P has L equal to 1, it has equal to L equals 0, have different energies. And these will not generate, and this is explained by perturbative quantum electrodynamics beyond the tree level. There is a minute difference between these two states. You see, the normal, if you remember hydrogen atom and its excitation levels, ionization levels is, I think, 13.6 electron volt. And this difference is micro electron volt. It's extremely small, but the experiments were precise enough to measure it. And the results came out that these kind of loop diagrams are which are corresponding when electron is talking to the proton at the same time, these things can be happening to these particles, and these are the things which are contributing to these lamp shift. So there is a lecture once I had given, which is called renormalization in 1 hour. It's not 1 hour now, we have 5 minutes left. So it's renormalization in 5 minutes, 10 minutes, maybe. There is a break, no? About 10 minutes afterward. So I think this is just one example. Let me just see it and then we will finish it. And this is something everybody would know because we all have seen classical electrodynamics at undergraduate level. So we'll be looking at this infinite line charge. Okay, line charge goes to minus infinity to plus infinity. Okay, and we want to calculate what is the potential at a point P due to this line charge, which is equidistribution of charge everywhere. And we want to find out what is this. And you'll find something amazing in this example. You see, what you do is that you take a little, how do you say, little element, a length element here, and you calculate what is the potential here. Because of that, it will be like 1 over this length, and then you integrate over the whole line charge. Okay, so that's what you do. This is 1 over r. There will be a charge factor here, and then you minus infinity to plus infinity. You factor these things out, and you only look at this term. Well, that's a completely crazy thing if you look at this thing. How do you calculate it? And what's the result of this? What is crazy about this is that it is dimensionless. You see, the unit dimensions of space cancel out with the dimensions of space. So how is the result going to depend upon R if it doesn't even have a dimension in it? So there are only 3 possibilities whenever such an integral arises which has no dimensions in it. The result will either be a constant, which will be finite, or it will be a constant which is infinite, or we have to introduce some other length scale which is relevant to the problem so that it can depend upon R. There is no other way because this result is dimensionless. So that's a very interesting idea that will eventually tell us about like the running coupling of quantum electrodynamics of quantum. They're no longer constants because you have to introduce a length scale eventually because of similar kinds of problem. When you do this, take your Mathematica or whatever program you have, you'll see that this is actually is divergent. The other thing is that it is translation invariant. You've introduced, because there are things I'll not see because of the lack of time, is that if it's an infinite length of wire, if you move it onto the right or the left, it will still stay infinitely long. So, you know, it's symmetric, you know, how much translations you do, nothing happens. If you really now want to do the integration, a finite integration, you have to introduce cutoffs, and you have all done it in your school, when your colleges, when you do that. You go from minus L to L, and you get this integration is log. Again, you see, if you put L infinity, it becomes infinite. Okay. The second thing, what you do is, what you have to remember is that now it depends upon R over L, because we have introduced the length scale here. For calculating the electric intensity, you take its derivative with a negative sign, and then it becomes this. Now you can take L to infinity, because in physical observable electric intensity, when you take L infinitely large, there is an L which comes from here. These things cancel, and this becomes 1 over R. Okay? And you all know that electric intensity is 1 over R. Perfect, problem solved. But when you do this, what you find is that this thing, you have to regularize it. You had to introduce a cutoff to make it possible for the potential. And secondly, that this result now no longer is translation invariant, because you have made a fixed length of it. When you have a fixed length wire, when you move it towards right or left, the potential at this point will not be the same. If it is here, this potential will be different. If this is lying here, the potential here will be different. Okay? So you have introduced translational non-invariance in it by introducing this cutoff and the potential. It doesn't matter to you, you would say, because what you're interested in is electric field intensity. But there are things in which you become it. There is another way of solving this. Don't introduce this length scale up and down. Change the dimensions in which you're doing this integration. Okay? So what you can do is the following. Imagine that this integration is not in 1 dimension. You're doing it in d dimensions, this integration. But again, when you change dx to ddx at a different dimension, you have to introduce another length scale so that your dimensions do not change. Because when you go to another d dimensions, you have increased the dimensions from 1 to d. So this thing does is this minus d cancels with d so that you still have the length dimensions where mu has the length dimensions. And then you make the integration, you make radial integration, and the other part you do the angular integration. And this is your solid angle in d dimensions. And you eventually put d equal to 1 minus 2 epsilon. I'm going to stop in 2 or 3 transparencies. So then you calculate this. And when you do the integration, you find this gamma functions that many of you probably already know. This is an extension of the factorial in real space. And when you put this d equal to 1 minus epsilon, that we are going only a little bit away from 1 dimension. Okay? And what you see is that this will depend upon this epsilon, which is when you take epsilon going to 0 limit, you'd come back to 1 dimension problem that you were doing it. But this has a pole at 1 over epsilon. And then you have this terms mu over r. Again, you're introducing a length scale. Okay, mu is a length scale here, not the mass scale. And its power is 2 epsilon. Again, you can do this derivative. Once you do the derivative, then from this, there will be another epsilon which comes here. And this epsilon times gamma of epsilon is not divergent anymore. Because this pole divergence of 1 over epsilon, which is in gamma of epsilon, cancel with this, and the result is again finite. But the good thing is doing this is that here, at no point you have lost your translational invariance. Your length of the wire is still infinitely large. So you move it left and right, the potential still remains the same. So your potential is not translationally non-invariant. So the good thing is that when you do this kind of integration in arbitrary dimensions, it preserves your symmetries of the problem. So that's the only message that I want to take. And some other thing that we will do is something called renormalization schemes you might have heard. You see, you had a gamma over epsilon in the potential. When epsilon is very small, that gamma over epsilon can be expanded in these terms. It's like 1 over epsilon plus some constant terms, and there are terms which are proportional to epsilon, which will drop out when you take epsilon going to 0. But this potential is as good as working with this potential in which you have removed this 1 over epsilon from the beginning. If you had never taken this into account, this 1 over epsilon, your problem still be the same as before. Because when you take the derivative of this for taking the electric intensity, this 1 over epsilon never entered the problem anyway. Okay? So what you say, this is a step called regularization, in which you introduce a parameter which takes an infinite part separate from the finite part of the problem. Okay? And this is called renormalization when you take out that infinity. Okay? And there are different ways of doing it. One is called the minimal substitution or minimal subtraction, in which you take this 1 over epsilon away, and the results are not, but just do it systematically everywhere in the problem. Okay? Or it is called an MS bar scheme, which we will be working it eventually, in which we find that, look, there is no reason that we take these two constants along with, because we are going to take their derivatives and they're not going to appear in anything afterwards. So we remove those as well from the beginning, because it's not going to affect any physical observable. Right? So when you remove those as well, along with 1 over epsilon, it's called modified minimal subtraction, because you removed a few constants as well. Okay? So that's what you can see, that you can do it in electrodynamics at classical level. And V depends on, the only thing is that this V will depend upon additional length scale. And that's all what happens. And that is what will translate when we are tomorrow going to see how we calculate the running coupling in quantum electrodynamics and quantum chromodynamics, how the presence of a charge changes the medium around it. There are virtual particles created through Feynman diagrams that we have around that. And when we go to do these loop calculations, which Lamb told us we have to do it, and which the theoreticians didn't know for a long time, and that will create lots of infinities here when we put this. But when we look at the charge of an electron, and if we want to really look at what is called the bare charge, we have to go deep down where the virtual particles are not present. Okay? So, and the physical charge, what we see in the lab, is surrounded by all these. Okay? So that's what we are going to see. We are going to introduce loops, and that will introduce divergences. Then we have to do the regularization of integrals, renormalization, and see what the charges look like. And just to have a glimpse of it, that when we do it for quantum electrodynamics, imagine if this is a vertex, an electron-photon vertex, but inside there will be so many loops and stuff going on. And then you have to regularize the infinite integrals. And eventually it will tell you that electric charge really is not a constant. We have to introduce a length scale that will make it depend upon that length scale, just as the potential in electromagnetism is. Okay? And that we'll see is that if there is a bare charge, then at different energies, at low energies, it is 1/137, as we have in the experiments. When we go to higher energies, it increases. In QCD, it becomes the other way around. Okay? When distances are small and the energies are high, it is very small. When the quarks are very close to each other, they don't interact with each other. They're quasi-free, but when they try to separate from each other, the interaction increases. That is because alpha starts depending upon a length scale, which we cannot avoid. As soon as we go to loops, we have to introduce a length scale. Otherwise, there is no way we can proceed to do our calculations. And that is all where I will probably stop. The only thing that I want to know is that there are a few calculations that you will have to know. And you can look at the lectures and see it because my time is over. For example, we will see this kind of integrals. We have already seen this integral for the potential. It just complicates a bit more. It's in D dimension, and where this is the denominator, and we do this integration, and you will find this result. Again, just as a function of, gamma function, and gamma depends upon this epsilon, which is 4 minus 2 epsilon. Just look at these things, and we will just need 1 and 2 denominators. This is for 2 denominators below. The final results will be again written in terms of some gamma functions, and that some of these gamma functions will have infinities, some will not have. And actually, in the last slide, it tells you how can you identify that which of these divergences relate to this ultraviolet divergences and which are related to the infrared divergences. Okay? And once you all know this, we can proceed to see how these things start playing a role when you go beyond tree level in quantum electrodynamics and then in quantum chromodynamics, and how this coupling changes and what parts of the coupling then becomes so large that we have to have hadron physics laboratories like the Jefferson Lab to study its effect and study hadron physics. That's it today.
Okay, let's, I think we still have some time to make 1 or 2 questions, so.
So when you are discussing the renormalization of steps in the minimal subtraction, when you avoid the constant, do you compare with the constant and you throw away which is the smaller in quantity? How is, so there was like 3 constants, 1 over epsilon, there was gamma, then log and right? So how do you decide which one to throw away?
You can only throw one. You can throw both of them. The thing is that those are the only 2 which are constants that do not depend upon epsilon. There are terms after that which will be proportional to epsilon. Those we generally don't throw because we will see that some of the terms which are proportional to epsilon will eventually cancel out with some of the 1 over epsilon coming from some other part of the diagram and will give you a finite result. But these ones will never do that.
The reason why we threw away again is because it was constant, and when you take the derivative, but there were also other constants. So to deciding which constant to throw away.
I don't think there were other constants. They were just proportional to epsilon. Oh.
Modified with gamma and so the log pi.
Gamma and log pi. You do one or the other, your final physical observable wouldn't change. The only thing which you're not allowed to do is that in one part you throw only one constant, in the other you throw both the constants. If you decide which constants to throw away, then you always have to do in every diagram the same. Once decided, always decided. Otherwise, I actually have a detailed example in which you try to mix up the things and that gives you the wrong results for field theory.
And is there, my question mainly was to understand like if there was any intuition behind picking which constant to draw.
No, there is not. It's just that some calculations are simpler done in one way and the other. When calculations become very messy, you just decide which to throw. In fact, that's what I will give an example tomorrow. When you decide about the coupling, it's easier to define in the MS part because right from the beginning, you don't worry about those concepts.
So when you introduce the Gauss field, could you remind what exactly those refer to the Gauss field? Yeah.
The ghost field. Oh God. Yeah. Yes and no. There is a lot of, how do I say? There's a bit of a freedom when we talk about the gauge fields. Imagine we're talking about a photon. Okay, photon, as you have studied in optics classes and all that, just have two physical degrees of freedom, the transverse degrees of freedom, the polarization. But we treat it as if it's a 4-vector mu. Okay, so we are giving it a lot more honor than it really deserves. Okay. And therefore we have some freedom of changing this mu without changing the dynamics of it. And that's called the gauge freedom. So we can choose to work in some gauge or the other gauges. There are different kinds of gauges in which we can work. There's Coulomb gauge, there is covariant gauges, there are axial gauges, and there are gauges that I've never worked with. There are light cone gauges in which some people will be working. But there are some gauges in which there is one of the quality of theory is unitarity. It gets is lost if you don't take care. So your S matrix is not unitary, S dagger S is not one. And therefore you have to use some how do you say, some fields which maintain at every step of the calculation and the final results that is not lost. And because we will be working in such gauges which are called covariant gauges, for that we have to introduce these fields to maintain this property of QCD. But then you can work in different other gauges which they will never appear and not needed to work with.
Andrew.
Oh, yes.
Yeah, naive question, I think, but going back to imposing local gauge invariance, I feel like as it was explained to me, it was, oh, look, we get local interactions of the gauge fields and the matter particles if we impose this, this symmetry. But that to me always sounded a little ad hoc, or like you already know you get the nice thing by imposing this symmetry. Is there any historical motivation for why one would see local invariance and say, let's make it also depend on space-time, and it should be invariant under this?
Okay, that's what I was trying to see in the very beginning. In fact, as I told you, this we knew the Maxwell's equations for a long time. And when quantum mechanics was invented with the with the Fermion field, a wave function, only a few years later than Schrödinger gave it, people started looking at it. The question is wrong. It says, please try again. No, saying that. I know. Yeah. So what was I saying? Yes. After quantum mechanics, when we know that in the Maxwell equations, you have to have electric currents, and those currents come from the wave functions of the electron. Psi bar gamma mu psi is the electric current, and that will feed into the current which with the A mu field of the Maxwell equation will work. And then it was in these 2 or 3 years people realized that all of this could be understood by this local gauge transformation. Okay. Now it worked in QED. We already knew what the Lagrangian was. It was just rediscovering the same Lagrangian through this local transformation. Now, how did we generalize it? I told you that when Zhang did his work in 50s, there was no need for doing anything else. But we knew that there was SU2 spin symmetry, isospin symmetry, SU2, and SU2 spin. SU2 spin was known for a long time for electron up and down. SU2 isospin was given by Heisenberg, and he said, oh, imagine what happens if I try to localize it. And it says, oh, I'm getting 3 fields. That's what he says. It gives birth to 3 fields instead of 1 we have in QED. But it didn't lead to anything because we don't have that. We didn't have that till 1954. When quark model was given by Gell-Mann in 1960s, okay, and when Nambu started working on it, even something like that. When eventually QCD came, then you could see from QCD that could be very well applied to SU3. The SU2 of the original work of Zhang didn't work, but QCD, which was as SU3, those could be generated through this local thing. And they lead to everything that we were seeing in the experiments. So that the trust for that. But that was in the 70s. But just before that, in the standard model, when the weak interactions came through something similar. In fact, in my opinion, the weak interactions gave us a lot more information, and the standard model, especially when the weak interactions are there, gauge transformations and gauge symmetry becomes a lot more important, extremely important. In the sense is that if you do not have your interactions with this local gauge transformations, your theory is no longer renormalizable. Okay, so you lose your renormalization, and that is partly what happens is that left and right-handed fields work a bit differently. Okay, people can still not worry about that much if there was just QED involved, but or just QCD. But when there are left and right particles involved and they behave differently under gauge transformations, then the standard model, if we do not have this, then we lose the renormalizability, and that's more sacred than anything else, because in that sense, if you're not working with effective field theories, then it means that you can't make predictions beyond that.